Welcome back. So, in the last lecture we had a very basic introduction to real time systems. What is a real time and what is a real time operating system, how is it different from a traditional operating system, and we had said that one of the major requirements for a real time operating system is that it should help the tasks meet their deadlines. And then we had seen that embedded applications are becoming numerous, and that is a important application area for the real time operating system. And then we were looking at what are the different types of real time systems, hard, soft, firm real time systems, what are the examples of that. And now let us continue from there and let us see what are the different type of tasks that a real time system might have to handle. So, a real time operating system, the tasks can be broadly saying three types: periodic, aperiodic and sporadic. A periodic task, as the name says, the tasks recur according to a timer. For example, let us say a chemical plant, the parameters of the plant are sensed periodically, and then the computer decides whether to take a corrective action, and if there is a corrective action like changing the temperature or chemical concentration and so on, it does within certain time. So, we will see that for all real time applications, the periodic tasks are majority. A large number of tasks are actually periodic tasks. We might have aperiodic tasks. The aperiodic tasks, they recur randomly and are soft real time tasks. For example, let us say an operator gives a command, let us say to increase the temperature or to reduce the rate of chemical reaction. So, when the operator will give a command is not known. It can be any time, can be a random, and also the response to this command is basically soft real time. Once the user gives the command, it may take several seconds and there is no hard deadline by which it needs to do it. On the other hand, there may be sporadic tasks which are again random, but these have hard deadlines with them. For example, let us say a fire condition occurs in a industry, in a chemical plant, then the sensors check the condition and they initiate several actions, maybe sounding an alarm, maybe stopping the reaction, maybe starting a water shower and so on. So, when such an alarm will occur, a fire condition is unpredictable, it is random, but then the action must be initiated within certain time for the plant to contain such an emergency situation. So, as we were saying, let me just recapitulate. We are saying that in any real time application, a vast majority of the tasks are periodic, some tasks may be aperiodic, and these are basically soft real time tasks. These occur randomly, and another category are the sporadic tasks. These are real time tasks, but they occur randomly, and these are rare. Aperiodic and sporadic tasks number is very less compared to the periodic tasks. Now, another thing that we want to mention is that the timing constraint on a task is defined with respect to some event. So, once an event occurs, then we start counting the time, and we say that before certain time the result must be produced, and the event may be either produced by the system or the environment. We will see examples of both as we proceed. In a typical application, there are a large number of real time tasks, and these get generated due to event occurrences. Some of these events may be internal events or may be external events. Just to give an example, that a task may be generated when the temperature sensor senses a high temperature. Then the task could be to reduce the temperature, maybe to start a water shower and so on. So, this event is got generated by an external event of temperature increasing to a certain extent. The internal event may be that maybe the memory out of memory, or maybe some task is taking too much time. So, those are the internal events. So, whenever a task gets generated due to an event, we say that the task is released or is generated, or we even say that task has arrived. Now, with this background, let us look at the real time task scheduling. In the most elementary description, we will say that the task scheduler decides on the order in which the different tasks to be executed by the computer, which one to be executed first, which one to be executed next, and so on. So, it is the task scheduler whose role is to decide which task to be executed next. And we have already said that the task schedulers are an important part of all real time operating systems, and they are the primary means by which the operating system helps the applications to meet their deadlines. As we look at different real time operating system, the first thing we will mention is that what is the type of the scheduler. So, every real time operating system, the scheduler is a very important component. Now, let us look at some very basic terminology, because we will be using this terminology as we proceed. A job is a unit of work. For example, perform a computation, like check if certain condition is reached or certain condition is satisfied, to read a file, to store some data, to communicate with another task, etc. These are example of jobs, and these are task instances, whereas a task is a sequence of similar jobs. For example, let us say one task may be to handle the temperature of the chemical plant exceeding some threshold value. So, each time the temperature sensor measures it and it periodically measures, a task is generated to check the temperature value, whether it is above the threshold, and then if it is above the threshold, then take some corrective action. So, every few milliseconds or so, when the temperature sensor gives its input through an interrupt, then the task gets generated. And when the task gets generated, we say that the task is released. So, that is shown here, that the task release time, and then the operating system starts to execute the task after some time. So, this is the start of execution, this is the release time, and this is the start of execution, and it may complete after some time, and then a deadline is associated with real time tasks, and if the deadline is measured and reported with respect to time 0, we say that it is a absolute deadline. Whereas, if the deadline is computed or is reported with respect to the release time, then we call it as the relative deadline. That is what we have shown here. The relative deadline is starting from the start release, task release to the deadline, whereas the absolute deadline is starting from time 0. In this area, that is a accepted terminology, that an instance of a task is called a job. A task is typically recurs number of times. Periodic tasks occur, they recur periodically based on some clock interrupt, whereas aperiodic and sporadic tasks, they occur randomly, and each time a task recurs, we say that an instance of the task or a job has been generated or released. And when the ith time the task T recurs, we say that the job or task instance T I said to have arrived. And we already explained the absolute deadline is the terminology we use to give absolute time to the deadline starting from time 0, whereas relative deadline is counted from the release of the task. So, this we already shown earlier. So, here because this is an important terminology, the relative deadline and the absolute deadline, just showing it again. From the task release to the deadline is the relative time, whereas from time 0 to the deadline we measure it, we indicate it by the absolute deadline. Now, let us define another important terminology that we will be using is the response time. The response time is the time from the release of the task till the task completion time. So, as the task is released at time t, the task execution starts after some time, and then it executes and completes at certain time. So, the time from release of the task to the completion time of the task, we call it as the response time. And we had said that, that in the traditional operating system, which handles basically soft real time tasks, the response time needs to be minimized. And even in a real time application, in a real time operating system, if the task is a soft real time task, we need to, the operating system need to minimize the response time of the task, whereas for the hard real time and sporadic task, minimization of the response time is not the objective. The objective is to meet the deadlines of the hard real time and sporadic tasks. For hard real time tasks, as long as the task completes within its deadline, there is no special advantage in completing it any earlier than the deadline. Now, let us look at another term, phase of a task, because this is also an important terminology. As we look at the task schedulers, we will often refer to this phase of a task. In any real time application, there are many tasks and a large majority of them are periodic tasks. But one thing to note is that the periodic tasks do not really start from time 0, many periodic tasks do not start. They start after elapse of certain time. So, the events keep on occurring here at certain time and then they start, but initially the task for some time does not exist. So, this is called as the phase of the task. Just to give an example to make this point clear, we will take the example of a rocket. So, once the rocket is fired, initially it goes on its own momentum for certain time, and then we do not have a task correction taking place. But after some time, the trajectory correction task starts. Let us say that the track corrections task starts after 2000 milliseconds of the launch of the rocket. So, the phase of this task, the task correction task, is 2000 millisecond, and then once the task starts, the first instance of the task starts after 2000 millisecond, and then it periodically recurs every 50 millisecond, and the execution time may be 8 millisecond and deadline is 50 millisecond. So, that is the description of this track correction task, that the phase is 2000 millisecond after the rocket is fired. For 2000 milliseconds, no track correction takes place, and after 2000 millisecond, the first track correction task starts, and then it recurs after 50 millisecond, and each track correction task requires 8 millisecond of execution time, and the deadline for each task once it is released is also 50 millisecond. We look at another terminology which we will also use, is the valid schedule and a feasible schedule. A valid schedule is one where the task is assigned to a processor, the task is not scheduled after it is released. So, only after it is released or generated, then the scheduler schedules it, and its constraints that it should precede some other task, etcetera, is satisfied. But then it does not say that whether the deadline will be met. In addition to these aspects, if the deadline is also met, then we call it as a feasible schedule. So, for a valid schedule, if the task deadlines are also ensured to be met, then we call the schedule prepared by the scheduler as a feasible schedule. We have another term as a proficient scheduler. We will see that given a task set for a application, some scheduler cannot really ensure that the tasks meet deadline, whereas there may be another scheduler which lets this task set to meet the respective deadlines. Then we say that the second scheduler is more proficient. We say that a scheduler S1 is more proficient than S2 if whenever S2 can feasibly schedule a task set, so can S1, but not vice versa. And two schedulers we say equally proficient if for any task set that one scheduler can feasibly schedule, the other scheduler can also feasibly schedule. And an optimal scheduler is one which can feasibly schedule a task set which any other scheduler can schedule. Now, we look at one more important point before we look at the standard schedulers, that is about the scheduling point. We can think of that a scheduler is a software component which becomes active at certain points of time and then decides which task to run next. So, on the points of time, at certain points of time, the scheduler task becomes active and then decides which task to run next, and these points where a decision is made regarding which task to run next is called as the scheduling points. Of course, in a clock driven scheduler, the scheduling points are defined by interrupts from a periodic timer. So, they will be placed uniformly on the timeline and they are generated by clock interrupts, and the scheduler becomes active as soon as the clock interrupt occurs and decides which task to run. On the other hand, in an event driven scheduler, the scheduler does not become active based on a clock interrupt, but it is based on certain events. As the name says, event driven, the events that cause this scheduler to become active are not generated by the clock, but by the completion and generation of tasks. So, if some task gets generated, the scheduler becomes active to check whether this new task which has come up, is it to be scheduled right now. And also whenever a task completes, the scheduler becomes active and then decides which task to schedule. We will see that the clock driven schedulers are simple schedulers, whereas the event driven schedulers are more complex, sophisticated schedulers, and they have many advantages over the clock driven scheduler. But the clock driven schedulers are the ones which are used in simple, cheap applications, whereas in sophisticated real time applications, the event driven schedulers are used. Now, let us look at the different schedulers that are available. Now that we have some basic knowledge on the real time systems, the task characteristics, terminologies of tasks, types of tasks, and so on. Let us look at first task scheduling on uniprocessors. Actually, task scheduling algorithms were the focus of the research in the 1970s and 80s. Lot of results became available during those days, and many of those results are even referred till now. So, based on the research done those days, we have mainly two types of schedulers. One is called as clock driven and event driven. So, if you remember what we said in the earlier slide is that if the scheduling points are generated by a clock interrupt, these are called as clock driven scheduler. So, here based on a timer, the scheduler becomes active periodically, and that is a clock driven scheduler. These are simple schedulers. Whereas, in an event driven scheduler, the scheduling points are defined by certain events. And what are those events? We said that there are two main events, the task starting event or release event and the completion events. So, we will look at various types of schedulers. One is that endless loop, it is just a simple program without an operating system. There are no tasks and it just checks certain conditions in a loop and then acts. And starting with no operating system, we have simple cyclic executives. There is a single frequency at which the tasks execute. The period of the tasks the same, and once a timer interrupt occurs, the tasks are taken up for execution and then the system waits. On a multi-rate cyclic executive, as the name says that there are multiple frequencies, different tasks arise with different periods, and we will discuss about the multi-rate cyclic executive and how does it handle these different types of tasks and help to meet their deadline. So, these two, the simple cyclic executive and the multi-rate cyclic executive, these are used in rather simple applications, whereas the ones that are sophisticated are the priority based preemptive schedulers. These are the event driven schedulers. We will discuss our good portion of our discussion is on the priority based preemptive schedulers, but in the next lecture we will discuss about the cyclic schedulers. Thank you.